Thank you. So welcome this morning. Actually, HVDC is nothing new. It's well known, especially here in India. We are one of the largest countries with one of the most highest numbers of HVDC applications. But I'm working now 25 years in this field of HVDC, but I have to say the last 7 to 10 years, HVDC, the role of HVDC has increased significantly, and one major reason is the role of integration of renewables in the world. And I would like to share with you experience we have, solutions, not solving all problems when integrating renewables, but I think HVDC can play an important role to help to integrate renewables successfully. My presentation, I would first give you a brief introduction on advantages of HVDC, why using HVDC. I would like to introduce different types of converters which have recently been developed and applied in the world. And then I would like to show how these different types of converters are used and configured and used for different types of integration of different renewables, and including hydro. I would like to give you specific examples of projects in Europe, in Germany, but especially also worldwide. And finally, I would conclude with some outlook on the latest innovations and what is going on in the near future. So, HVDC is, as I said, well known. There are three major types of applications of HVDC. Most common is the long-distance transmission, where HVDC is used as a very efficient way to transport our energy over long distances. And we heard power system strengthening is one of the important tasks when integrating renewables, because in most cases renewables are located far away from the load centers. Second application is use of DC cables. So if energy has to be transmitted via cable over distances more than 30 to 50 kilometers, then DC is the only method to do it. And we see this now also increasing, not only for connecting offshore wind farms as an example, but also a number of land cable applications is increasing very much. The first application will be also here in India, and Siemens just got the order to construct a transmission in the southern part of India this year, and this includes 30 kilometers of land cables. And last application is back-to-back links, which are used to connect different not synchronized AC systems and to exchange energy between both systems. So what is the reason why HVDC is used there? And HVDC is not replacing AC transmission, but it's complementing AC, where AC is not so beneficial. So most important, of course, in many cases of projects is that HVDC is chosen because it's the most economic solution, especially if we talk about these long distances, what I said. It's just an economical decision in this case. One important aspect in this case is also the reduction of losses, because DC is more possible to transmit more power over long distances on the same right of way. So that is also now an increasing application that we see worldwide. The number of new overhead line transmission to be constructed is limited. There's a lot of opposition. Yesterday it was mentioned, especially in Germany, but all over the world this tendency is going on. So we have to really find ways how to use the existing right-of-ways in the most efficient way. Next is that we can control, and there, especially also in Germany, HVDC can play an important role, or will play an important role. Existing systems which are already highly developed need to be expanded with this new power trading or energy trading, energy transmission schemes. And so in order to enhance existing highly meshed systems, HVDC can feed power in a very efficient way because power can be directly controlled. So the way to avoid circulating currents is avoided. And finally, also different systems, as I mentioned, and this is also used in India, back-to-back systems can be used not to interconnect directly different AC systems, but to exchange power without increasing the short-circuit power. So the existing power infrastructure can be further used, even if we have a larger number of generation in the same nodes. HVDC, and especially the fast control of HVDC, is very beneficial in order to control the power flow, steady state in both directions in a very accurate way. But it can be used also in order to dynamically enhance the stability of the power systems. And that means we can control not only the frequency by changing the power schedule of the DC link. This, of course, is somewhere limited, and we heard this just in the presentation before on the example from Denmark, where power is exchanged with Norway, for example, between different systems. So you have to rely that the other system has enough reserve capability, but you can control and use the power, if this is the case, very efficient to control also the frequency. In parallel, HVDC can also control the voltage by changing the reactive power demand, and especially the new technology, the voltage source converter technology, is very powerful to have a fast way, and this is acting similar like a STATCOM in this case. Let's look on the two major technologies nowadays on the market on HVDC. On the left side, you see the thyristor-based so-called line commutated converter technology, based on the thyristors, which are on the market since the end of the 60s of last century. We have possibility to construct systems with bipolar systems with capabilities of reaching up to 10 gigawatt per system, bipolar system. So it's a very powerful system. Siemens is using direct light trigger thyristors, very robust thyristors. Voltage levels now have been developed and are in operation also in India. The first schemes are in operation up to 800 kV DC. In China, 1100 kV is currently under development. So there's actually a large capability of such a system to transport a huge amount of energy and power. This is the most efficient way to transport power over long distance, bulk power. However, there's one restriction, and that means that this technology is not suitable for all applications, especially if we look on some applications for renewables, which is that the system strength has to be at a certain level. Also, some requirements are there regarding space requirements, and I will give you some examples to give you some impression on this. The disadvantage of these powerful thyristors is that they can only be turned on. They are turned off by the system strength, or by the AC system. This is complemented now by the second technology, which is now in broad application worldwide since 7 years now. And it's called voltage source converter technology. Siemens brand name is HVDC+. There, instead of thyristors, semiconductors are used, which are the IGBTs, which can be not only turned on, but also turned off. That has a major advantage that we can control the DC link independent of an AC system. So even a weak AC system is possible to be operated. Even islanded AC systems can be operated. And that's really the core application for such technology. And in Germany, in Europe, offshore wind farms is one excellent example where this technology is used very successfully. So the wind farms are setting up an own islanded system, and the DC can operate very stable with these wind farms. Also, additional advantages of this technology is that XLPE cables can be used because the voltage is not reversed. And we can also easily construct not only a point-to-point connection, 2 terminals, but also multi-terminal, or even in future, it's a little bit the outlook, DC grids in the future. Currently, and that is a little bit the disadvantage, this technology is still in a fast developing, evolving stage. Power ratings are much smaller compared to thyristor technology. However, right now we can supply systems, bipolar systems, up to 2 gigawatt. I would like to first give you some examples of the thyristor technology, LCC. There's one link in southern part, east-south interconnector of India, where what Siemens constructed, and the configuration is what is most common in LCC schemes is a bipolar link. So we have 2 conductors, plus minus, bipolar voltage, 500 kV, plus minus in this case. You see, it's basically a series connection of 2 converters, 2 times 500 kV, and in the middle there's a ground potential. There can be another conductor in the middle, which is a neutral bus conductor or neutral conductor. So this is a highly flexible scheme where you also have some kind of inherent redundancy. If you lose one converter, for example, you can still operate the second one at 50% power. For this east-south interconnector, a most economic way has been chosen by not installing a third conductor. So the return current is in this case forced to go through ground via ground electrodes. This is possible also for C connections by C electrodes. However, I have to say nowadays it's very difficult to get permission to construct new ground electrodes or C electrodes worldwide. So in many cases, the new schemes now are designed with a third conductor, metallic return conductor. Another example of such a bipolar scheme, now at a highest voltage level in operation worldwide, is 800 kV. First one was constructed by Siemens in the year 2007 or 2008 in operation, and it's transmitting a typical example for transmitting large amount of hydropower from the mountain area in the center of China to the load centers in the on the east coast. So transmitting 5,000 megawatts. As I said, nowadays even 10,000 megawatts are possible. You see here on the picture, unfortunately, it's a little bit small on the top side. This is quite a large area, such as a converter station requires in the hilly mountain area. So a large amount of this area is due to the number of AC filters and reactive power compensation equipment we need in order to compensate the operation of the converters. So that's one disadvantage or one requirement, that you need to have enough space if you choose such a topology. There are different ways in practice how to construct an 800 kV scheme, and all of them are somewhere applied in the world. On the left-hand side is the most simple one. It's well known to you. It's just the bipolar scheme what I mentioned before with a metallic return conductor. We are currently constructing such a scheme in Brazil to transport also a large amount of hydropower. It's the most economic way because only 2 converters are needed here for each converter station. However, there's one disadvantage, of course. The larger the amount of power is, the larger is the impact if you lose one of the converters. So 50% of power is lost if one converter has a problem. This is improved, and if you look on the middle and the right-hand side of the schemes, by adding additional converters, so putting in series 2 converters to form up such an 800 kV converter by 2 400 kV converters in series, for example, or it could be, as you see on the right-hand side, also 2 800 kV schemes, converters in parallel. The middle one is a typical scheme, how schemes are designed in China. And it's a little bit, of course, it's more expensive compared to the left-hand scheme. However, there was one also practical reason why to choose such a technology or topology, is that the large transformers could not be transported to site. As I mentioned, this is a hilly area, so transportation limitation was forcing also to divide the power into smaller units. Lowest losses are, of course, on the right-hand side, and this is one scheme as it is used also here in India, 2 times 800 kV. That means also if one converter is not in operation, you can still continue to operate at 800 kV, which means minimized losses for the whole scheme. So that's just an overview on different possibilities how to construct UHVDC, ultra-high voltage DC applications. The last example I would like to share with you on the LCC is one link we are currently constructing in the UK, on the coast of UK. And here again, application is wind in Scotland is generated. A surplus of wind is available there, and load centers are in the southern part in England and in Wales. And there was a restriction of transmission path inside UK, and so the only possibility was to use the sea cable solution. And Siemens decided to or proposed a very cost-effective way to transmit here a large amount of power. And you see here again a configuration which looks like a bipolar scheme, what I mentioned before, but here the return path is missing completely. So we call this a rigid bipolar scheme. So because the current is always forced to flow through the 2 high voltage conductors. So you save installation of a third cable, which is quite a high invest for such a long cable. With one disadvantage, if you lose one converter, you have to interrupt the power transfer and make some reconfiguration and restart the system again after. So this means an interruption of 2 to 3 seconds. I would like to go now to other applications for integration of wind farms in Europe and in the North Sea. I just mentioned in Scotland a large amount of wind. We heard about Denmark, a large amount of wind. We have also a large amount of wind in the North Sea by offshore wind farms. And Siemens is very proud to be the market leader in constructing a connection of the wind farms. And this includes both the AC connected wind farms offshore as well as DC connected wind farms. So you see here a large amount of farms which have been constructed. The slightly green ones are the ones which are closer to the coast, which are connected via AC. So STATCOMs are typically also supplied there on the connection point on land. And the blue ones are the DC links, which are constructed by Siemens. So presently we have 4 large HVDC offshore links in operation in the North Sea, and 2 further ones are under construction. Just to give you an impression how such a VSC converter, voltage source converter, looks like, it's a very modular scheme. IGBTs are put into, time is very short. I have to speed up a little bit. So I go a little bit through the pictures so that you get an impression of the converter. This is a converter hall. Major advantage is that such a converter hall is now, if you compare to the picture I showed you before, no filters are needed anymore, so a very compact converter station, so that you can design it also on a platform, as I mentioned here. And the configuration here shown is a symmetrical monopole, which means just a single converter with 2 cables, plus minus, similar to a bipole, but a single converter, just to give you some impressions. The largest scheme currently in operation is in Alpha project, is 2 times 1,000 megawatts connecting France to Spain. Also exchanging renewable energy. A lot of solar in Spain is generated, so it's exchanged to France via VSC. There's an overview on all projects, so a large number of projects in Europe, but also, as I mentioned, the first one now in India. And that is more the conclusion also, an outlook on the new applications. This is a picture of Germany where we just heard also yesterday a lot of energy, wind energy is available, not only from offshore in the North Sea, but also on land side in northern part, and the load centers are in the south. So a lot of new transmission solutions are needed to transmit this energy to the south. And Siemens got the order to construct the first link on the left-hand side called Ultranet project. And what is new about this project? 2 things, and then I will conclude then. One is we are using here a new topology of converters, which are called so-called full bridge converters. So this is suitable to operate a VSC also on an overhead line and to extinguish any faults due to lightning strikes on the overhead line, causing DC faults in a very fast way. So a built-in feature in the converter itself. And what is also, I think, quite interesting is we are using here a hybrid tower. So we're combining AC and DC on the same tower, which, as far as I know, is the first application worldwide since ever. Yeah. Last thing is we also introduced now offshore solution also to make a platform more compact by introducing DCCS, we call it. It's a DC GIS system, very compact system, allowing to make platforms more compact and more cost efficient. So I see a lot of new applications on the field of HVDC since the last years, and I see this goes on, and I'm very convinced that such a solution can help also India to provide adequate solutions to integrate renewables. Thank you very much.